Well, good morning. It is Monday morning, April the 27th. It's good to be back for another week of school. And it is a beautiful Monday morning. I just finished biking into work and it was just a fabulous bike ride. The sun is shining, the birds are singing. It is a really, really good day, and it looks like it's going to be a good day all the way through. And this morning, I just want to start you off with our verse of the day, which comes from Psalm 46, verse 10. It is a good verse. It's one of my favorite Psalms, one of my favorite verses, and here it is. So Psalm 46, verse 10 says, "Be still and know that I am God. I will be exalted among the nations. I will be exalted in the earth." So let that be our prayer today. I want you guys to be still, know that God is there, that He will be exalted, that He is exalted, and that He is in control of all things. So that's what we want to focus on today, and let's get into our lesson for the day. All right, so here are the answers from the assignment that I gave out last Thursday from page 386 out of your textbook. I gave you questions 15 to 21 to do, and here are the solutions from fairly straightforward questions. If you remember that there are two formulas that are really the same formula. They're velocity, distance, and time formulas. And so we have our kinematics velocity formula where velocity equals distance over time, and we have a wave equation for a periodic wave that is the velocity times the wavelength, velocity equals wavelength times frequency. So when we look at these questions here, in the first question we have a sound wave that's being produced 515 meters away, and we're hearing the sound 1.5 seconds later. What is the speed of the wave? Well, velocity is distance over time, 515 meters, 1.5 seconds, 343.3 meters per second is the speed of that sound wave. Now, the speed of sound is not a constant, but it's in the same realm, same region, same ballpark, right? So it'll always be in this low 340s-ish number for the speed of sound. We have a unit on the speed of sound coming up, and so we'll learn some of the factors that affect the speed of sound. But in air, the speed of sound will be around this 340-ish, 343 mark in the low 340s. So you can kind of always know whether you're getting that right if it's the speed of sound in air. Second part of the question is, if the sound wave has a frequency of 436 hertz, what is the period? Again, period and frequency are inverses of one another, and so the period is 1 divided by the frequency. 1 divided by 436 gives us 0.002 seconds, because remember, period is the time for one cycle, so it's always going to be measured in seconds. And then the third part of that question asks us for the wavelength. I've done that over here. Again, using our periodic wave formula, solving it for wavelength, for lambda, we get V over F. So 343.3 divided by 436 gives us our wavelength of 0.787 meters. All right, moving on. Question 18. Again, fairly straightforward question asking us for the speed of a wave that has a frequency of 3.5 hertz and a wavelength of 0.7. Quite simple. Here's your formula. Got to remember this formula. 0.7 times 3.5, 2.45 meters per second. Question 20, we have to be a little careful in reading the question. We have 5 pulses being generated every 0.1 seconds. So we have pulses in 0.1 seconds. So we can find the frequency. Now, in order to find, the question's asking us again to find the speed of the wave. So to find the speed of a periodic wave, we need to use V equals lambda F. So frequency is the F. We need to have the frequency. The 5 pulses in 0.1 seconds gives us the frequency. 5 divided by 0.1 is 50 hertz. So that becomes my frequency. We have 1.2 centimeters per second. Sorry, 1.2 centimeters for the wavelength. Make sure I got that right. Yep, 1.2 centimeters. 50 hertz is our frequency. That is 5 divided by 0.1. All right, multiply them together, you get 60 centimeters per second. If you change this 1.2 meters, that's no problem. You'll get 0.6 meters per second. No problem. And finally, question 21, again, fairly straightforward question. Question gives us a frequency, gives us the distance between successive compressions. Now remember, a compression is in a longitudinal wave where we have a compression. A compression is equal to either a crest or a trough in a transverse wave, and so the distance between successive ones becomes our wavelength. And so the wavelength is 0.6. The frequency was 20 hertz. Gives an answer of 12 meters per second. Hope that makes sense for you. We're going to move on. So we're going to move on now to talk about some wave behavior. And again, this is in your textbook. It's section 14.3 in your textbook, page 387, and a few pages past that. Just a few things that I want to point out. We're going to look at what happens to waves when they approach boundaries. We'll consider a boundary, it could be either a hard surface that it bounces off of, it can be nothing, that if it's transmitting in a medium like a spring where it can come back without actually hitting anything on the other end. And we got on the other board, we've got some diagrams of what happens when a wave moves from one medium into another medium. Because again, the medium that a wave is traveling through affects the speed of the wave, primarily. It affects a few other things too, but it affects the speed. So, first of all, there's two kinds of reflection that can happen with a wave. Now, these are waves moving in one direction, straight there, straight back. We'll get into two-dimensional waves at a later on point. But for now, we're just doing one dimension where it's just going backwards and forwards. And so here we have what we call a fixed end reflection. A fixed end would be like this spring that I have right here. It is attached to something at the far end over there, and that is a fixed end. If I was hanging the spring vertically, so this other end of the spring that's hanging vertically, where is it? There it is. Okay, if this was my attach point here, this end would be a free end. If I were to create a wave up here that would travel down, then this here would act like a free end. It's not attached to anything. So that's the difference between fixed end and free end, and the reflection is slightly different depending on whether you have a fixed end or a free end. When you have a fixed end reflection, the incident wave, the incoming wave, coming this way, hits the boundary, hits the fixed end, and it reflects back inverted on the other side. And you can see that when we create a wave, I don't know if you can see this or not, I might put it far enough back, but if I create a pulse, you can't see it. Look back at yesterday's video where I created the wave pulse. When I showed you the transverse wave, you'll notice that as the wave traveled toward the fixed end, it was on top of the spring and on the bottom as it came back. All right. When we have a free end, when it's not attached to anything, then it reflects back not reflected. It reflects back in the exact same manner that it came into. So if it's above on the top half of the medium, it'll come back on the top half of the medium. That's what happens when we have boundaries, whether it's a fixed end or a free end. Let's go look at what happens when we have a wave traveling from one medium to another medium. So here what I've got is I've got a wave traveling from a light medium where the wave would travel fast, moving into a different medium where the wave would travel at a slower velocity. All right, so what happens when this happens, when a wave goes from a fast medium to a slow medium, both the speed and the wavelength have to change, all right? Because the frequency, if it was a periodic wave, the frequency wouldn't change. So if we don't change the frequency, but we change the speed, then the wavelength must also change to make it work. But what happens, what we want to do is what happens when the wave hits this boundary between them. So here we have a wave. I forgot what direction. This wave is traveling in this direction, and it's before it hits the boundary. So here it comes in, and it hits this boundary. What happens after it hits this boundary is diagrammed in this second one. Okay, the pulse that started here, it continues. It just keeps going. It's going to move at a slower speed because now it's in a slower medium. But it also will get reflected back this way. And because we're going from a fast medium to a slow medium, this boundary between them acts like a fixed end reflection. All right, so it goes in, it keeps going, but part of the wave gets reflected back. And so the amount of energy that was here is now split between these two waves, so the amplitudes will be different. And this wave would have an amplitude, these two waves would have smaller amplitudes that would equal that amplitude there. Okay, so the energy is still the same, because again, we know from other physics stuff that we've done, or you've done science stuff in the past, that energy can't be created or destroyed, and so we have to have the same total amount of energy, but part of it keeps going forward as normal, part of it is going to get reflected back as a fixed end reflection. Now, if we were to reverse this, if the original wave started here and was traveling this way, okay, from a slow medium into a fast medium, then what happens is this boundary would act as a free end reflection. Okay, so that's a slight difference. Again, the incident wave would continue. So if we were to change this now, okay, where this was our before picture, okay, where we had it going from a slow medium into, so this wave would be moving this way. What happens after the fact then is, again, the wave will continue moving this way, but in our slow medium, it'll still be above, but going backwards. Okay, so got the E on before. All right, so the slight difference, okay? Again, when you have the original one that we just talked about. Here's a new one now. The original wave, the incident wave, the incoming wave, whatever you want to call it, is coming in from a slow medium, going into a fast medium. When it hits this boundary, the original wave will continue on with a smaller amplitude, but the reflected one will go back, but it'll be, again, in the same manner above the medium. In the reflected pulse, because this boundary will act as a free end. So going from light to heavy, from fast to slow, we have what acts like a fixed end reflection. Going from slow to fast, it acts like a free end reflection. Hey, we have one more principle we want to talk about. Let's go do that on the other board. Here now I want to talk a little bit about the interference of waves. When we have more than one wave in a medium, and those two or more waves are interacting with one another. So a common example is radio towers. Radio towers emit radio waves that go out from a tower, multiple towers, and they approach each other and they interact with one another. Those wave crests and troughs interact with one another. And when they interact with one another, they interfere. Okay, and so there are some principles there that happen. First of all, there's two kinds of interference that can happen. There's constructive interference and there's destructive interference. So what happens is if we have a wave that is traveling this way and another wave that is traveling that way, what happens is when those two waves go through each other, and they will continue to go through each other. While they are going through each other, their amplitudes will be added up, and that would be constructive interference, okay, where their amplitudes are added together. So if this wave had an amplitude of 1, and this wave had an amplitude of 1, when they passed through each other, it would be one wave that would have an amplitude of 2 for that moment while they are overlapped, and then they would continue to move past each other. So constructive interference happens when the two waves come together while they're together, and then the two waves will continue on again. All right, destructive interference is exactly the opposite. What happens is we have a wave traveling this way and a wave traveling this way, where they are on opposite sides. Now when they pass through each other, they're going to have what's called destructive interference. This is a destructive interference. This is a crest meeting a trough. Destructive interference is when the amplitudes subtract from one another. All right, and so as these two waves pass through each other, their amplitudes would add up as well. But in this case, they would cancel each other out for that moment. So what you would see is if you had a wave above and a wave below, as they went through each other, all of a sudden, if it was in a spring, your spring would go flat for a moment, and then the waves would continue through each other again. It's kind of cool to look at, kind of cool to watch. If you have a really long spring at home, or a string even, you could test this by creating pulses at either end of the spring or string and watching them as they go through each other. Okay, now, the other point I've got on here is nodal points. Okay, so with both constructive and destructive interference, it can be partial or complete. What that means is that as these two waves go through each other, right, at the first bit, maybe it's half plus a half, giving us 1, right? There's various points on here where the wavelength, where the amplitude isn't exactly 1. You would have partial constructive interference, and then it would be complete constructive interference when they were exactly overlapped, and then they would move through. Complete destructive interference, again, is where the waves completely cancel each other out for that moment. And when we have complete destructive interference, we get what's called a nodal point. So this is complete destructive interference. Okay, so when the wave cancels each other out, we have a nodal point. Okay, now I'm not drawing this very well, obviously, because I'm not a very good artist, but in your textbook, between pages 387 and 389, there are some descriptions of this, and there are some really good diagrams, much better diagrams than I can draw. All right, so what I want you to do is I want you to read those sections. There's no other homework today other than reading a few pages in your textbook and trying to understand some of these properties of waves that we've been talking about here today. Okay, so again, those pages are 387 to 389, talks about free and fixed end reflections, talks about waves at boundaries, talks about interference of waves, okay, with constructive and destructive interference, a little bit about nodal points, and it also talks a little bit of something about standing waves. I'm going to get you to read it, and maybe tomorrow, I will show you a little demonstration again. I'll try to create a standing wave in the spring that I have here, and you'll be able to see it. But they have some really good diagrams again, and you'll be able to take note of that. So that's your homework. Read those pages. Hope it goes well. Ask any questions that you have. Send me an email if you have questions. If not, we'll see you tomorrow.